Hey everyone, I'm Chuan Hao, founding engineer at Tandem, and today I'm going to talk to everyone a bit about networking technologies and how they enable us to have fast inference between two nodes. So today specifically I'm going to talk a bit more about internal communications between two GPU machines. So for example, if I have one machine, GPU machine A and then GPU machine B, and the internal communication between them. So as all computer science students will know, there's classic communication between two machines, like for example TCP/IP. But in the data center environments today, with all the HPC technologies, there's also things like InfiniBand, or even ROSE, which is a RDMA over Converged Ethernet, and a lot of this proprietary kind of technologies that help users data center networks to improve networking between nodes. So today specifically, we're gonna discuss a very interesting technology released by AWS in about 2021, and it's called EFA, which uses this protocol called SRD, which is Scalable Reliable Datagram. And this technology is particularly interesting, and today we'll dive into it a little bit. But before we get into that, let's take a look at TCP and why it's not enough really for today's inference workloads. For example, as we know about TCP from back in school, TCP enforces two key properties. One is reliability, so that your packets are guaranteed to be sent across to the other side, they are acknowledged, they are retransmitted. And the second thing is that they're transmitted in order, which means that if I send out packets A, B, C from here, they will come in A, B, C on the other node. And this is nice when in the 80s when TCP/IP was invented, because we want to communicate two machines over the public internet, where the routes between two machines are not fixed and packets may arrive out of order and things like that. But in a data center network, things actually looks a bit different. So particularly TCP/IP isn't very suitable for HPC kind of workloads. Why does that happen? And one of the big reasons why TCP/IP is not suitable is because of the in-order property. So for example, in HPC workloads, a lot of it depends on many nodes. For example, say I have nodes A, B, C, D, E. A lot of HPC workloads depends on synchronization between A, B, C, D, E, where they will all reach a certain point together at the same time before they can all proceed to the next phase of the computation. And reaching this shared point together requires a lot of internal communication between all 5 nodes. And the thing about TCP/IP and enforcing in-order packets is that if one packet fails to arrive at one node, for example, if I want to send packets 1, 2, 3 to node E, but packet 3 arrived first, and packet 1 to 2 did not arrive, the node itself will not receive any packets at all. The TCP stack in the kernel will actually hold on to the packet that it received and deliver no packets to the nodes. And because this one node is stuck, the whole HPC workload is now blocked on that one node. So this in-order property of TCP ends up being a problem for HPC applications. So today we're going to talk a bit about, like I said, EFA SRD, and how data center networks enable us to do this a bit better. So for example, in a data center, nodes aren't connected just like this one-to-one actually. In data centers, for example, AWS claims to use a clause topology, where the nodes actually look like, so for example, AWS says that they use a clause topology, where the nodes, for example, between two nodes A and B, they're actually connected to a bunch of switches, which is then connected to more switches, right? And imagine if I drew lines to everything. And we call this layer of switches the spine, and we call this layer of switches the lifts. So what this means is that there's actually many equal duration paths from A to B. You can go through here to go here, you can go through here to go here, and things like that. And data center networks do this to maximize bandwidth between two nodes. And this enables us to do different things with the network rather than just normal TCP/IP. For example, in AWS, they use ECMP, which is equal cost multipath routing. To send packets from A to B. And what this means is that in ECMP, it actually hashes the flows. So it knows some information about node A, it knows some information about node B, it knows some information about the application that is trying to send stuff from A to B, and it will hash that and use that to determine maybe a fixed path from A to B, like that. And for the rest of the same application, all the packets on the same application, ECMP tries to use the same path to go from A to B. And it becomes quite obvious why this is bad, because now we're not using all the available bandwidth that such a topology provides. So one good thing about SRD is that it kind of changes the packets. So SRD manipulates the packets so that packets of the same flow, of the same application from A to B, actually can traverse different paths. They can go through this one path, they can go through another different path to go to B, right? And it can essentially exhaust all the available paths from one node to a different node, right? And so there's one benefit of SRD. Well, the side effect of doing something like that is that, for example, if node A wants to send packets 1, 2, 3, 4, 5 to node B, it can actually send packet 1 on path A, packet 2 on path B, packet 3 on path C, and so on. And the side effect is that all the nodes will take the different paths and arrive at B in whatever order they come in. So this is one example. So to kind of reconcile with this, SRD doesn't actually does not guarantee in-order delivery. So this gives so SRD as a protocol, transport protocol, does not guarantee in-order delivery of packets, and it is up to the application on the other side on the other node to determine whether it needs in-order packets. And this turns out to be fine for a lot of applications, because not every application needs the packets to arrive in the same order as it was sent. So second, so we've mentioned packet spray and we've mentioned in-order delivery. So one last optimization that SRD has One last optimization that EFA SRD have in AWS is that they're implemented in custom AWS Nitro networking cards. And from a software perspective, the stack looks like this. So instead of the traditional path where it goes from application to your kernel TCP/IP stack, and then in AWS this goes to your ENA network interface. How it actually looks like will be like this. So your app goes to the lit fabric library, which is common for a lot of HPC applications. And this will actually go to a custom AWS EFA kernel driver. So this is the boundary between kernel space and user space. And this will actually go to your AWS custom Nitro card. Since the custom card is exposed to the OS as a custom PCIe card with its own driver, it actually can offload a lot of this processing within the custom card, and this reduces a lot of OS overhead such as context switching, system calls, and jitter, and improves the network throughput from one node to the other node. So this is how AWS uses EFA and SRD to achieve high bandwidth and low latency communication between two nodes. So thank you for joining us on this journey today as we talk about EFA, and we'll see you in the next video.